Now let's talk about service chaining. Service chaining is an important buzzword today. In this image, a host sends a packet through the network toward the server past D. This packet is carried through some edge network and into the edge router at the provider, marked as B in the diagram. And the provider has a set of policies about specific operations that have to take place on the packet or the flow before it can be forwarded to D, the ultimate destination. Now, to implement these policies, the provider puts an appliance in the path of the packet, such as a firewall, which is C in the diagram. Pretty familiar, yes? But what does the firewall appliance really do? The firewall actually provides a set of services, such as NAT, DPI, VPN Access Control. Do all these services need to be in a single appliance? No, they don't. Let's split these individual processes up and then put them on generic hardware. After all, we have a data center fabric sitting somewhere with a ton of compute space and storage. It's easy enough to spin up a VM that can perform NAT, for instance. In fact, deploying a set of applications that each individually perform one of these three functions, NAT, DPI, VPN Access Control, onto generic x86 computer resources in data center fabric, it's a pretty simple concept. Now, if the traffic that needs to be DPI'd increases, we can scale out rather than scale up by simply spinning up more VMs. Now, these processes aren't in the path of the traffic flow that I'm trying to apply the services to. So how can I resolve this? I can't readily push each of these services into the shortest path between A and the destination, D. If I can't bring the services to the packets, why not bring the packets to the service? Network Function Virtualization, NFV, allows for the services within the box to be pulled out of the box and run on off-the-shelf hardware. What if I could, at A, determine the set of services through which this particular flow of packets must pass on its way to the destination past D? What if I could attach labels on the traffic from A so that it would be sent to each of the various service VMs as it turns and passes the traffic through the center data center fabric and before being passed to D to continue its journey to the actual destination? This, in essence, is what service chaining is all about. The NFV could be in the data center, or with the right hardware, it can be on the SD-WAN appliance locally. With service chaining, a label will actually cause the network to forward the traffic to the first service in the chain, which then pops a label and forwards the packet along. Second label causes the packet to be sent to the second service, if there is one, and then pops another label on and forwards the packet along, and so on. So this is simple, and it's a powerful idea, and it allows you to use NFV to, in theory, run your entire routing and security stack on a single server. But today, service chaining most commonly is used to leverage the cloud security services such as Zscaler and others. It allows us to virtualize services into generic data center fabric, running a service on a standard compute and storage. It allows us to insert and remove services easily just by spinning up VMs and pushing the right stack of labels at the network entrance. And finally, it allows us to scale services by spinning up VMs and using scale out rather than scale up principles. So what's the cost of using a service chain? As packets find their way through different services in a chain, there's latency introduced. And if the services are running on the same hardware, that delay may be negligible. But if the service chain runs through a remote cloud service, the latency introduced could be more significant. Now, if the cost of the network is cheaper than the cost of the appliance, plus the cost of installing new hardware to roll out a new service, then service virtualization and service chaining is clearly a winner. Other trade-offs to consider, besides the additional latency and delay through the network, the actual cost of generic hardware to meet your compute requirements, and the additional complexity of the traffic engineering involved per flow. But SD-WAN helps make service chaining possible and manageable.